Hello everyone. I have set up some LEDs here, and I have 3 sets of 8 LEDs all lined up in a row. And what I want to do is to have them light up sequentially one by one. And to achieve that, I'm going to use 2 chips, or 4 in total, but 2 kinds. One is a 4-bit binary counter, and the other is a decoder or demultiplexer. And I'm going to have 3 decoders. So let's go check out the binary counter. I have the data sheet right here, and this is for the 161 and 163 binary counters. And there's a subtle difference between the two, but an important one, and we'll look at that. For this application, I've chosen the 163. And it's also the data sheet for the HCT and the HC technology. Now, there's we gotta go look at this Art of Electronics book to see the difference between these 2 technologies. They're both CMOS technologies, so they both use those CMOS types. But if you come over here to this plot here, it kind of shows a history of different digital IC technologies. The bipolar TTL was a famous and very popular one back in the day. And because it used BJTs, you can see the dividing line between high and low logic is not in the center, right? I mean, we go from 0 to 5 volts, and so you think a high would be from 2.5 to 5, and from 0 to 2.5 for a low. But in fact, the low is only from 0 to 0.8, whereas the high is from 2 to 5, and the midpoint is like 1.3 or something. And that just has to do because of how the BJT works, and like the voltage drop from the base emitter and stuff. But we won't get into that. In the CMOS technology, that's the HC version. You can see it's much better. It's right down the middle, and that just makes more sense. If you have 2 states, and you're operating from 0 to 5, well, you should just cut it right in the middle. Now the HCT is the one. Well, it's just the chips I have, so that's why I'm using it. It's for no other reason than that. I mean, the HC is probably a better choice because of this even division. But you get all the benefits of the CMOS chip, except they have this version just so that it could be compatible with the older TTL, since they were so popular before. And so it has the same logic division as as the older TTLs. And that's like the main difference between the 2 technologies. Okay, continuing on. So let's go check out this this binary counter. And here we have like the pin layout. So we got our ground and our power supply. Okay, and we have this Q0, 1, 2, and 3. And this is going to be the output, the output of our 4-bit counter. So it's going to count from 0 to 15. So when it's all full of 1s, that's 15. And then once it reaches 15, it's just going to go back to 0 and count up again. It's just going to keep on going in a circle like that. And you have this little TC pin here, and what that does is that's a signal to when the counter is full. So when all of these become 1s, this guy lights up and he goes to 5 volts. And it kind of says that, I'm full, I can't count anymore. And it could kind of be used to like daisy chain other similar chips, or the same chip really, if you want to count beyond 15, right? So you also have this TE and PE pins over here, and those are just the enable pins, and both of these need to be tied to 5 volts for this chip to be counting. And if either one of them goes low, then the chip stops counting and it pauses at whatever count it's currently at. And right here we have the CP pin on number 2, which is the clock. and that's what kind of tells the chip to count. And I've drawn a little clock over here. And the important thing to note is that the chip increments at every positive edge of the clock. So it's not just, oh, it has to be high and it's going to increment. No, it's only at the positive edge will the count go from 0 to 1, and then over here from 1 to 2. Okay, moving on. The MR pin, pin number 1. This is the master reset pin, and you see it has a little bar over its name, and that means it's an active low. And so if we want to reset the pin, if we want to reset the count back to 0, we got to set the pin low. And here's the difference between the 163 and the 161. In the 161 chip, the moment that this pin goes low, these outputs jump right to 0, and they're all set to 0. However, in the 163, once this goes low, it has to stay low until the next positive edge of the clock. And when that positive edge comes up, only then does the output get reset back to 0. And that's called a synchronous reset, whereas the 161 is a jam-loaded reset, because the reset happens the moment this thing goes low. And if you look at this SPE pin over here, again, it's got another bar. And what this does is that it loads, it could preset a value into the output. And that's determined by this P0, 1, 2, and 3. So you could put any binary number from 0 to 15 here, and when this goes low and stays low until the next positive edge of the clock, at that moment, on that next positive edge, it's going to load whatever number you've put on these inputs into the output. And so you could just load up a number here, and this gives you a bunch of flexibility. So you don't have to count from 0 to 15 every time. You know, you could count from 6 to 10 if you wish. You just basically load 6 up once it reaches 10. You know, you set a little signal, oh, it's 10, put this guy low, and then on the next positive clock, if you have 6 loaded here, it will load up 6. And so it kind of gives you flexibility in that regards. Okay, so that's the pinout, and that's kind of the how the chip operates. So let's check it out on the breadboard, which I got set up right here. Okay, so these 4 LEDs represent the output. So we got Q0, 1, 2, and 3, and they follow these yellow wires to the pins over there. Of course, we have our power pins right here on either side, and this red wire connects the 2 enable pins, the T and PE pins. And so for our chip to work, we're going to have to set both of these pins high. I've just connected them together, so we only need to use one jumper to set it high or low. And right here, you see I have 4 grounds here. This is the normal ground for the power, but these 4 grounds are for the P0, 1, 2, 3 chips. And our SPE pin is right at the edge here. And so if this is ever set low, then all it's going to do is load zeros into the output. Now, I'm not going to really use the load, at least yet. And so, but I still tied them low because, you know, for chips, you never want to leave the inputs just floating. You want to set them high or low. Even if you're not using them, you want to put a value on them. You just don't want to be floating around in the air. That's not good. And our clock pin is here, and the master reset pin is here. And this little green LED, if you follow this orange wire, that's that TC pin. So this will light up to say that the count is full. So basically, when all these reds are lit up, this will light up too. Okay, so let's set up our control pins. So first, we have the enable, and we got to put that to high. Okay. We have our master reset right over here, and we have to put that to high as well because that's the active low. Right? If we want to reset the pin, we have to put it to 0 volts. We don't want to reset it yet, so we keep it high. And it's the same story for this load pin. That's active load too. We don't want to load it up. We put that to 5 volts. And of course, our clock pin. So I'm going to come here to our clock and connect it to the clock pin. Good. Now let's put on some power. And now the chip should start counting as it does. And you see it started at a random count because you never know what it's going to do once you power it on. But now it's counting, so it's going from 0 to 15, and you see the little green LED lights up when all the other LEDs are lit up. And the rate of the count can be controlled by the clock. So if I start speeding up the clock, well then, you know, it starts counting faster too. And of course I could just slow it right back down so you can see it actually count. And that's how it goes. So let's look at the load pin. Actually, to do that, before I do that, I want to add a big fat cap on our clock. So this is going to slow our counter right down. And basically, this is just going to demonstrate that it's in, like, the moment this lights up, you see it change. So it really is right on that rising edge. And let's take that master reset. The master reset, like I could reset it right now, but it's only going to be on the rising edge. Doesn't go to 0. And so it's just important to note that it's the rising edge of the clock that's what counts. So we could go back to normal mode, take out that fat cap. And of course, here's our enable pin. So if I pull this out, wait till I get to a number, then it's just going to, oh wait, and I put it to ground, of course. Then it's just going to sit at whatever number I've set it to. And if I go back high, well, it's going to count again. You notice it also keeps counting. Oh, see now, there it does. But it's you don't see it's erratic. That's why you always want to have your inputs either low or high, because you just can't trust them to do something. You want it to count, you put it in the 5 volts. And it's kind of the same with, say, the master reset. If I pull it out, is it going to reset? Oh yeah, but then it counts 2, and then it's just going to reset randomly. So always put something on the inputs. Don't have them floating. All right. And now to the clock pin, which is the most, it's the most critical signal, and it's the most sensitive one. If I were to pull out the clock pin and just have it float, you see the output kind of goes haywire, and it's just doing whatever, some craziness. Now if I ground it, there's no clock pin, and it just doesn't do anything. If I take it out and I put it in high, on the 5 volts, it's the same thing. It stops counting, because even though it's at a positive voltage, it's at a logic 1, it's only on that positive edge that it does something. Okay. Now, as we go along in our project, we're always going to want to take special care of this clock pin. Clock signal. So I've added a little 1 kilo ohm resistor here, and I'll put the clock on this side. And so it's working fine because the kilo ohm resistor isn't going anywhere. So it's just like a wire. However, if I add a capacitor to it, you'll see that it's kind of acts erratically. You see, it's not really counting correctly. It's kind of doing whatever it wants, really. And what we've done here is just put a low pass filter, and basically now our positive edge is not so straight. And that's what kind of messes up the count here. And to see that better, we could put it on the scope. So I've attached two oscilloscope probes. One is right here on the clock signal, the yellow trace, and the blue trace is on the first output, so that first Q naught. So here all I have visible right now is our clock. And it's doing as we would expect. It's going up and down in a square wave. And in this configuration, I have not added the capacitor to make it a low pass filter. If I had the capacitor, this is what the clock looks like. So you see the overshoot is gone, and it's curving a little on that edge. And now it looks pretty much like a square wave. It doesn't look like a big change. But if we zoom in, it'll show all the difference. And so now it's at 200 microseconds of division, and so you can see the curviness of our clock. If I pull out that cap, he shoots straight up, and now his back is straight, and he's no longer a hunchback. Now let's make this guy visible, and let's trigger on our Q1. So again, this is without the capacitor. The capacitor is not added, and we have our regular straight back clock. And the Q1 is showing just what it should be. It's essentially twice the size of our clock. And there it is. It looks good. If I increase the frequency, you can see even more. And now let's see what happens when I add in that capacitor. So now it starts acting around, and it starts moving around a bit. And if we zoom in, it should help us see what's going on. Oh yeah. So it's kind of going crazy, right? It's like it's going up and down, and it's very erratic. And we saw on the LEDs that it's obviously not counting correct. It's doing whatever it wishes, and it's kind of, this fuzziness is terrible. And the problem is because our clock is rising so slowly, and that it doesn't know, it kind of gets confused, and it doesn't know what to do. Right now you can see the yellow trace, it's about 1.5 volts, and so for this particular chip, that's the dividing line from a high and a low signal. And so normally you want your clock signal to shoot right past that dividing line and make it clear, but since he's just like going very slowly in this up close view, very slowly through that dividing line, the output of the counter is confused, and he's just going up and down because he doesn't know what to do, and it's called a metastable state. And the moment I pull out the capacitor, then he's good, right? Now our clock rises up nice and fast, and so does the output. He's no longer confused. He's like, oh yeah, you're going up. I gotta go out. I gotta go up too. And so that's the importance of the clock signal. It's very important. And you might ask, well, yeah, just don't put a capacitor on your clock signal. And of course that's correct. We would never do such a thing. But the truth is, and let's just turn this off for now. I have all these blinking lights. But the truth is that in our circuit, sure, this capacitor has been designed as one, but really, anytime you have just metal close to each other, that's a little capacitor. And all these breadboards, these are just tons of little pieces of metal, all very close to each other, and it's kind of called parasitic capacitance. And so the bigger our board gets, the more parasitic capacitance there will be. And sometimes you'll see that happen to your clock signal, and you'll be like, you'll be wondering, hey, what's happening? Why is my counter, or, and it's not just counters, it's basically any chip that takes a clock signal and works on that positive edge. Any one of those chips, you know, that situation can happen if there's like, for whatever reason, there's too much parasitic capacitance, and your clock signal is not rising up fast enough. You could get that metastable state and that erratic behavior from your chip. And so as we go on and build our circuits, it's something to look out for whenever stuff kind of goes wrong. You always got to make sure that the clock signal is correct and sharp. And that's it for the counter chip. And so now let's go check out the decoder.